So the next speaker is an all known, is Óscar Moriones, and he will present his work on dual labeled core shell polystyrene nanoparticle with plasmon-enhanced properties as a model for the risk assessment of nano and microplastic. Thank you very much, Óscar.
Good afternoon. Thank you very much for letting me present my work here to the organizers and to everybody. Well, my name is Óscar. I'm from the Inorganic Nanoparticles group from the ICN2, and I will present this my work entitled Synthesis of these dual-level polystyrene nanoparticles with properties in order to the assessment of nano and microplastics. So nowadays, microplastics are a primary environmental concern, and it's because they are everywhere, in the food, in the environment, in the water, and they're very resistant to degradation, also can enter to our bodies through the food chain and the additives and some components and monomers that in which these microplastics are prepared are toxic. No, so that is why reliable detection of these microplastics is essential in order to a good evaluation of the plastics. So the microplastic detection basically rely on two techniques. First, the electron microscopy to detect the microplastic in the subcellular and cellular level with spatial resolution. So it's really interesting. And the spectroscopic methods such as Raman, infrared spectra, and gas chromatography for detection of the monomers. Robust techniques and really good ones, but present limitations when detecting because the polymer particles have a poor contrast brought in biological systems. In addition, doing techniques such as chromatography present complex extraction and cleanup steps. Additionally, the techniques need to be validated and calibrated. Also, the microplastic present this chemical heterogeneity by means that they have these broad sizes and different types and shapes, and this complicate things. And finally, they can undergo processes such as aging, aggregation, and fragmentation. So because of this, the level-free detection of microplastic is challenging. Using fluorescent specific labels are a good approach. For instance, fluorescence or radio labeling labels for in vitro techniques such as confocal microscopy, or for in vivo techniques such as positron emission tomography for a real-time monitorization of the microplastic in living organisms, but also present limitations such as photostability of the fluorophores and poor tissue penetration in biological systems. So a multimodal labeling for imaging will be really interesting. With means of multimodal imaging, I mean building a polymeric model comprising labels for different imaging modalities. For instance, we can comprise a metal with fluorescent molecules in order to build a multimodal contrast agent, which will help us to detect the microplastic by X-ray imaging because of the metal, and additionally by elemental analysis by ACPMS, and also the metal have a good scattering of the electron for the microscopy, and the fluorescent dyes with the confocal. So comprising this or combining this, we can reliably monitor the microplastic in tissues, organs, and cells for doing biodistribution, accumulation, and fate and secretion pathways. In the state of the art, there's scientists who are putting dyes with polymer particles, for instance, such as polystyrene, a lot. And in additionally, in the market, there's fluorescent and microspheres and bead with dyes and different sizes of polystyrene. But these present limitations because not present multimodal labeling for correlate with different techniques. In additionally, the dyes can be attached on the surface, so this gives a different identity. Also, if the environment is harsh, could be a leaching of the dye from the matrix. And finally, it will be a possibility to affect the photostability because some of the dyes are pH dependent. So only knowing all this background, we came up with a rational design of our particle. We need a particle for X-ray imaging and for fluorescent optical, with optical properties. So for X-ray imaging, we come with a metal. Gold. Gold is a really interesting metal because present high X-ray attenuation, so we can be followed by imaging. X-ray imaging, high density for the microscopes, are good optical properties and be identified by elemental analysis, and we can control the size following the localized surface plasmon resonance. And for the fluorescence, we came out with another interesting material, silica. Silica is biocompatible. It has been proved to be excellent as optical proofs, present a variety of cross-linkers, silane molecules, which gives functionalities, amino, carboxyls, among others, and it have a well-reported synthesis. So combining these two to build a model, we came up, or we designed a core shell structure in which in the core is going to be the gold nanoparticles with a silica layer with the dyes in the matrix for achieve a plasmon-enhance properties, multi-component material, and high compatibility because the silanes give you all these functionalities by means, because if we want to grow a polymer shell, polymers are hydrophobic, so we use a silane as a cross-linker to achieve these vinyl groups on the surface. And finally, with the emulsion polymerization, we can develop these dual-level polystyrene nanoparticles using a radical ionization and the monomer. So let's see the synthesis step by step. So first, I synthesize the gold nanoparticles. So I use the principle of Torskevich. Basically, I reduce a gold salt using the sodium citrate as a reductor and also as a stabilizer to nucleate and grow the particles. But in order to achieve our desired size, we applied a well-reported seeded growth method from Bastos et al. And with this, we achieve a very monodispersed particle, which around 66 nanometer in size by macroscopy characterization. And the UV spectra shows the localized surface plasmon resonance around 540 nanometer. And also the hydrodynamic size were correlated with the electron microscopy. Then we need to attach the dyes. But if we approach a dye to the metallic surface, such as gold, we can have a quenching effect. So in order to avoid this quenching effect, I said, okay, let's grow a silica first layer in order to create this space. So the silica will help us as a spacer. So I apply a stubber method in this technique in order to achieve a 30 nanometers of silica as a spacer, no? And the UV spectra is really useful because allow us to follow the interaction or the behavior of the gold nanoparticles. And as we can see here, there's a small redshift indicating that something was attached on the surface. And also this was correlated by the DLS or the hydrodynamic size. But why 30 nanometers of silica? Why not 10? Why not 40? This has something because we investigate the plasmon-enhanced fluorescence. So I took these gold nanoparticles and I grew a silica layer from 10, 30, 30 and 40 and 20 nanometers. And I measured the fluorescence of this particle and this nanocomposite and comparing them with the dye in solution, with the free dye in solution. Right? And we achieve a plasmon-enhanced fluorescence around 2.5 with the fluorescence with a shell thickness of 30 nanometers. Then once I achieve this 30 nanometers, so I incorporate the dye in the matrix, applying a second stubber using the aptes as a cross-linker, and we achieve these particles of around 200 nanometers of size by electron microscopy. And as we can see here in the UV spectra, we can see that a small redshift again from the gold, but with the appearance of the fluorescent band around 495 nanometers. And we correlate the size also by the DLS hydrodynamic size. So once we have this, we additional grow and silica layer in order to protect the dye. Why? Because the emulsion polymerization to grow this polymer is in high temperatures, and temperatures also damage the dyes. In addition, they use radicals initiator to polymerize the polymers. In this radical also can attack the dyes. So I wrote an additional silica layer in order to achieve this particle of around 250 nanometers. And as we can see by the UV spectra, again, we have the band of the fluorescent with the band of the gold. with the peak of the gold, correlated with the dynamic scattering. And finally, I wrote this polymer layer using the emulsion polymerization reaction, in which I used as a radical initiator the potassium persulfate and as a monomer styrene to be polystyrene. And I achieved this dual label nanoparticles using for multimodal imaging. I characterize it by electron microscopy, having a size distribution of around 536 nanometers. In the UV spectra, we can see the specific scattering or high scattering of the polystyrene, burying the signal of the gold and the fluorescein, and also correlating the hydrodynamic cycle. So we further go to test these particles in order, if possible, to use it as a multimodal contrast agent. So in collaboration with Muriel Freixenet from the Valdebrun Research Institute, we performed the in vitro, in vivo evidence of these particles. So we characterize well the particles, we make sure about the endotoxin contamination, which was negative, and then we conjugate this particle with albumin for 24 hours, and we expose it to the cell lines in the multi-wet slide, and we saw in the confocal microscope. And the confocal microscope gave us interesting results. In the first big image, we can see both signals, because in this photo was put in the reflectance mode and also the fluorescent mode. So there's the both signals located in the extracellular space, cell membrane, and the intracellular. But trying to do this spatial correlation to see if this signal is from our particles, we separate them and we put in the first image the fluorescent mode, and we can see the fluorescence of the fluorescent. But then we change it in the same spot, and we change in the two reflectance modes, and then we see the scattering of the gold particles. So with this, we can clearly say that this signal comes for our particles. But also, in addition to that, we do intravenous injection of these conjugated particles, and we collected the liver to do this embedded paraffin block. And the results also are really interesting. The nanoparticles were located in the subcellular structure, and again, both signal in doing this spatial correlation, we can see that in the fluorescent mode, we collect the fluorescence of the dye, but in the reflectance modes, also we are collecting the reflection of the gold, looking in the same spot. But for further correlate our results, so we work with Laura Mondragon from the José Carreras Leukemia Research Institute to continue with this in vivo experiment. So we took all the organs and also the feces of the injected mice to do the elemental analysis to correlate also the confocal ones. So interesting results by the ICP-MS following the gold said that basically we are in the liver with a concentration of 8 micrograms per gram, and also in the spleen. So this correlates the previous confocal in which the nanoparticles were in the liver section. But to see if we recover all the gold injected, we put this in percentage, and we can see that almost 95% were present in the liver of the gold, and also 4%, around 5% in the spleen. So we recovered almost of the gold. And to further combining another interesting technique, we do an oral administration by gavage for around 4 and 24 hours to do the X-ray imaging. And also we do elemental analysis to correlate results. And we see that the oral result or oral administration, the gold nanoparticles were located around in the stomach and in the intestine, but the pathways that follow basically were with the secretion for the feces. And trying to see if we recover all the gold injected, we see that 2% was in the stomach, but this is for about 24 hours, obviously. We're also in the intestines, but the majority of the gold was in the total feces, so was expulsed. So let's see the X-ray imaging scans. So the X-ray imaging scans show us that in the first 4 hours after the oral administration, the nanoparticles of this multimodal imaging contrast were located in the stomach. Those two small white signals are the gold nanoparticles and doing in the coronal axis, but contrasting this result with the axial axis to outrule the signal for possibly from the vertebra, we see that they're present in the stomach. And as we recall, the ICP-MA results for the oral administration basically were in the stomach, in the intestine, in the feces. And finally, after 24 hours, we can see that the particles are not longer in the stomach, now are in the large intestine. So this, again, we correlate the results from the ICP-MS with the secretion pathways was this. And also the actual results show that the particles are located in 24 hours in the large intestine. So a conclusion, we effectively address this microplastic issue, developing a new class of plasmon-enhanced particles of polystyrene with dual mode capabilities. We can successfully assess both in vitro and in vivo models, correlating the result of 3 or 4 techniques. Additionally, our methodology relies on the controlling of the chemical affinity of the components, and it can be customized to user, different size and other dyes. And finally, as a perspective, interesting to increase our multimodal contrast agent to a broader polymeric materials, such as PVC, PE, or PMMA, or PET. This is our research group. Thank you to all of them and my supervisors for this hard work. And thank you very much for your attention.
Thank you very much, Oscar, for the talk. And now it's time for questions.
Thank you, Oscar. Very nice presentations. So I have 2 questions. The first one is about using the seeded growth factor to synthesize of the nanoparticles. Do you have some key factors about this synthesis? Because also before I used this method to synthesize 40 nanometers of nanoparticles, but sometimes it's just a field. It's a really easy field.
Sorry, can you repeat again a little bit louder, please?
Oh, sorry. I mean about the you using the
seeded growth method
yeah,
for the ball, yes?
Yes, I mean if you for this, if some key factors just affect of this synthesis, because for me sometimes it's easy
Yes.
just
Yes, I understand. Yes, this synthesis have 2 main components. First one, once you reduce the gold salt in order to nucleate the first seeds, because in the beginning there's seed formation, you need to control first the temperature. The temperature is a key factor. If you decrease the temperature from around 100 nanometers to less than 90 Celsius degrees, sorry, less than 90 Celsius degrees, you can avoid secondary nucleation. So if you applied a lot of heat temperature, you will increase this barrier of energy and will put the gold salt to generate new nucleus, to say. So you need to first decrease the energy to avoid secondary nucleation, and also you need to control the pH of the reaction, because every time you inject with the gold salt to grow the particles, the pH is going to be decreased. If you achieve a pH around 4, the particles are no longer stable and maybe can aggregate. So you need to control pH and temperature.
How did you just control the pH?
I'm sorry?
Mean, how did you control the pH?
The pH of the solution
Yeah.
is because this is a seeded growth method. In every step, you have to wait around 30 nanometers after you inject the gold salt in the solution. So when you inject the gold salt, you wait this 30 nanometers, then you take a liquid, go to the pH meter and measure. If the pH is lower than 5, you need to add a base solution in order to increase a little bit the solution, or add more sodium citrate, because sodium citrate also increases the pH of the solution. With this, you can follow
Okay,
the
thank
pH.
you very much. And another question is about the down label, the cautious nanomaterials. So for this one, first these have the
Louder, please.
absorbance properties, yes, and also have the fluorescence properties. So this is functional nanomaterials.
Sorry, I don't. The echo don't let me to hear you well. Sorry.
Yes, 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 and I mean, did you just try using these materials as optical nanomaterials for the detection stuff?
Which one? Mhm.
Yes.
Yeah,
Yes,
if we
exactly.
consider this to use into both techniques, you mean?
Optical
Yeah, also they
application.
can be used optical application. One of my conclusions is that this kind of a multi-layer of core shell particles are customized to user. If you only want the dyes, I can put the only dyes to optical application. Or for instance, if you want the metal, also I can put the metal only for X-ray imaging or for element analysis. So I can basically control what components are going to be inside of the polystyrene. If it's only the gold, if it's only the silica with the dye, or both.
Okay, so because you just mentioned this plasmon-enhanced properties, so compared of the individuals like gold nanoparticles, all the fluorescent materials, what's the advantage of this?
You mean? The problem is if you put, let's say, the fluorophore close to the particle, you're going to have some drawbacks as a quenching effects. But but if you only put dyes alone
Yeah.
on the polystyrene particles, you are going to lose these multi-constraint agent capabilities. That's why we put both, not only dyes.
Okay.
Yeah.
Okay. And for the absorbance, like because gold nanoparticles can absorbance of the light, if for this one also enhanced only. Ah, quenching, yes. Okay. Okay.
Yeah,
Okay.
before putting the dyes, I would tune the space between between the metal particle and the dye with a
Okay.
silica spacer.
Okay, thank you.
By tuning the distance between the fluorophore and the dye. Okay, it was another question.
Thank you, Oscar. It's really interesting. I'm quite pleased to see so many such work on this. My question is in the studies, the toxicological studies, there was a comparison without any labeling of the polymer without any labeling of polymer. So the control particle, let's say, without if they
Dyes
use
alone, for instance.
sorry
Or you mean with dyes alone or with a metal particle alone or you with a polymer
a polymer
alone?
itself to see if my question goes in the direction of to see if the effects and the toxicological effects are similar without any labeling and with labeling.
Well,
I mean, not. I know that there is the purpose is to monitor, to follow, but just to see the toxicological effects of meaning toxicity, cell viability, and all these kind of
yes,
things.
not yet. This one was the first step of the work. First, we need to develop and standardize a model that allows combine 3 techniques. But now we are going to try to evaluate the cell viability of the cell expressions and the toxicity of these plastics.
Oh, okay.
In this step of our work, we only were developing the monitor the material. We can let's say to correlate 3 to 4 techniques.
Yeah, great.
Don't kill me, but if I can add something, I mean, the idea is that, so the point is that we use this method to label the microplastic. So, and then we were sure that the label was in the inner part of the particle, meaning that after exposing the particle to the same biological conditions, we couldn't see the release of the dye. And this is a critical point. And regarding with your question, Soko, there are a lot of studies on cell-based studies on the toxicity of the microplastic. The idea of Oscar, it was more in line of obtaining the biodistribution and obtaining the place where the particles are in tissues. goes a little bit.
No, but my question is to compare. So, because you are putting a label that you are now, what you are testing is that ensuring that, doesn't release, and to me is, it follows the same pattern as the one that is without labeling. I know that there is studies, but it's just to compare with yours so that your labeling is not affecting any pathway or any distribution. So if it follows the same pattern. So.
The thing is, our label is on the core of the polystyrene, so really protecting with that polymer shell. So in the market, is a model like this, a multi-contrast agent like this, is not have been used for toxicological studies.
Thank you. We need to move to.
Hi, Oscar. Thank you very much for such a nice presentation. I just want to ask you, how did you individualize the silica particles, since they are only 15 nanometers, and I know that they are really tend to aggregate. So how did you manage to individualize them? And then another question is, during the second covering of the silica with polystyrene, did you check the pH, and what was the pH of the system?
When I broke the polymer shell on the silica, I functionalized the surface of the silica with a silane cross-linker, which convert this methacrylate, it's called methacrylate silane, which convert these vinyl groups on the surface. And basically this particle becomes hydrophobic immediately. So they need to be dispersed in hydrophobic solvents. So no need to check the pH. The pH did not dissolve the particles. The multiple polymerization reaction is a tricky one because use radicals and use temperature, and this can dissolve the silica. So the nucleation of the polymer on top of the silica, and the top of the multi-contrast agent, need to be also fast. So I have a really hard time trying to control in timing, the perfect timing before dissolving silica and growing the polymer. That's why I put the external layer of 20 nanometers, because it was really complicated.
Okay, so I think that we need to thank Óscar again for
Thank
his
you very
nice
much.
talk. Please.